The other form of vaporization is boiling. And boiling, of course, is where the gas forms down below near where the heat is, and you get bubbles. So the atmospheric pressure plays a role in this because in order for these to escape, they have to also overcome the pushing down of the atmosphere. The lower the atmospheric pressure, the easier it will boil. So vapor pressure is a measure of their tendency to leave. And when that pressure is equal to the atmospheric pressure, that's when boiling occurs. So let's see what that has to do with how that affects boiling point. So when we say boiling point, it's the temperature at which boiling starts to occur, the actual bubbles. Remember, vaporization, or in the form of evaporation, occurs at any temperature because it's just leaving at the surface. But atmospheric pressure affects boiling. So if the atmospheric pressure is lower, then the vapor pressure can be lower. And so boiling would occur at a lower temperature. You're pushing against less, is the way to think about it. If the liquid has stronger attractive forces, like hydrogen bonding versus dispersion attractions, if they're more stuck together, then the boiling point will be higher as well. So let's look at an example where we can put together some of these properties. So looking at these molecules, the first thing is let's decide what type of attractive force each one would have, or the strongest type that it has, because they all have dispersion attractions. All you have to have is atoms and you have dispersion. But anyway, so let's look and see, can any of these hydrogen bond? And so what we're looking for is that I see this one has an OH bond right there, so it can hydrogen bond. This one has an oxygen, but it's not bonded to a hydrogen, so it can't hydrogen bond, but definitely it does form a polar bond. The C to O is polar. Oops, it's a polar bond, but the attraction type is dipole-dipole. And again, you know, it's kind of like I told you, anytime you see two different elements, you're going to suspect that that is polar, unless it is C to H, carbon to hydrogen. Okay, and then on this one, this was a hydrocarbon. It's a non-polar molecule. Know that about hydrocarbons, carbon and hydrogen only. So it only has dispersion attractions, the weakest type. So I kind of have them in order here, that this has the strongest attractions, and then weaker as we go this way. So the lowest boiling point, this means that it's easy to boil. You don't have to heat it up very much before the molecules can separate from each other. So that's going to be, the lowest boiling point is going to be C. It has the weakest attractions. That's what I'm looking for. And the highest boiling point is going to be A, the ones that are really stuck together tightly. You're going to have to heat them a lot before you can get them to the gas phase, which means they have to be separated. Okay, another thing, and I don't think this was in your book here, but I want you to know the basics of a phase diagram and how to interpret it and so forth. So a phase diagram is at a, for one substance that's at equilibrium, what states will you find it at if it's given time to switch phases as it wants to, and so forth. So basically, you know, like you could choose a temperature and a pressure and say, if given time, that material will be in the gas phase. It'll all evaporate. Or that material will all be in the solid phase. It won't. So anyway, we need to label these three colors by phase state of matter. So at low temperatures and higher pressures, what state of matter would you expect that to be? And at high temperatures and lower pressures, what state of matter would you expect? And then liquid is in here. And so along these lines are the temperatures and pressures at which that substance could be at equilibrium. Okay. And the triple point is this point here, where at that temperature and pressure you could potentially have all three states of matter in equilibrium with each other. Okay, so let me show you how we might use a phase diagram. And there are all kinds of phase diagrams. There are phase diagrams between different crystal states and stuff like that. So it's something that it's good to be able to interpret, apply this. So first of all, the triple point is where this orange dot is. So it's at 30. It's where they all intersect, degrees C and 1 atmosphere. If you want to pause me and answer the next two questions, you can. Okay, vapor pressure at 40 degrees C. So if we're at 40 degrees C here, and we're taking a vapor and compressing it, so this is pressure going up. So I've got a gas, remember gas is vapor, and we're compressing it. That means it's going to eventually become a liquid. And we could do the same thing if we have a solid at 0.5 atmospheres. So I'm in here, just following through 0.5. And I warm it. Warming it means I'm doing this. Then it will become a gas. In other words, that solid, when it's warmed, won't melt to a liquid. It will become a gas directly.